Welcome everyone. Thanks for joining our webinar today, Optimize Your IC Design Cycle, how multi-coax cable assembly helps engineers test cleanly, reduce components, and save money. We're going to get started with the presentation. Before we do, however, we want to just run through the agenda today. So we're going to look at some housekeeping notes. We'll introduce you to Arden Concepts, who we are as a company. Then we'll introduce you to our presenter, Gordon Vinther, CTO of Arden Concepts. We'll talk to you a bit about the challenges to engineers, such as signal integrity requirements, PCB overpopulation, and cost-prohibitive surface mount components. We'll look at Arden Concept Solution, the TR Multicoax Series. And then we'll look at some case studies where TR Multicoax was able to solve some of the major obstacles for our customers. And finally, we'll finish up with a Q&A session. We've scheduled an hour for the webinar, and we recognize that your time is valuable, so we'll do our best to hold ourselves to that time frame. So just a few notes to go over. There will be a Q&A session at the end of this presentation. If you have a question, please add it to either the chat or the question box, and we'll do our best to address all the questions. If we're not able to answer your question, we will be following up with you directly after the webinar. This session is being recorded, and a link to the recording and a copy of the slides will be emailed to you within a few days of the presentation. And at the end of the presentation, you'll be asked to take a brief survey. Please fill this out so we can provide you with future content that will suit your needs and to help us improve upon the process. With that said, I'm going to talk a little bit about Arden Concepts. Arden was established in 2003. We're headquartered in Seabrook, New Hampshire, which is north of Boston. We're a leading provider of innovative interfaces up to 70 gigahertz for high-speed electronics, and we'll be talking a little bit about that 70 gigahertz threshold today. Really, the goal at Arden is to strive to support the industry's leading applications with continuous innovation, and some notable firsts that I think are worth mentioning. We're the first 70 gigahertz plus solderless compression mount multi-coax connector down to a 0.8 millimeter pitch, signal to signal. We've patented our RC spring probe contact wire form and all subsequent contact technologies, and we have over 20 plus patents. We're actually one of the first to be using manufacturing connectors using rare earth elements for use in quantum computing. So these applications are so leading edge that one customer told us they wouldn't even be commercially viable for another 10 years, and we're working in those environments. We were the first to use wire forms for RF and compression interconnect. And lastly, we're the first to make a high node count, low force, all metal interposer using these wire forms. So again, just looking at some of a history of our innovation and our goal to continue to support the ever-increasing bandwidth needs of our customers and of the industry. With that said, I do want to introduce you to our presenter today, Gordon Vinther. Gordon is President and Chief Technology Officer and a founder of Arden. Gordon started Arden with the philosophy that engineering breakthroughs shouldn't be limited by the tools available in a lab or a production environment. And he directs all the R&D at Arden with a focus on developing revolutionary patented connector technology, enabling integrated circuit manufacturers and systems integrators to bring to market the fastest, highest performing computer systems. And prior to starting with Arden, Gordon had worked for Everett Charles Technology, where he designed a custom pogo-style interfaces there. So any of you working with sockets have probably used one with pogo pins inside of it. Gordon took this knowledge of interconnects and pogo-style interfaces, and he used it to look at how he could develop contacts that would be able to handle the industry's growing bandwidth needs, and that's kind of how Arden Concepts was born. He's since amassed over 20 patents in this time with Arden, and that's really a testament to his commitment to making Arden the world's #1 multi-coax manufacturer and supplier. And so at this time, I'd like to welcome Gordon Vinther to the webinar to take over the discussion. And again, just a brief reminder that we will hold a Q&A session at the end of the webinar, so please submit your questions to the questions box.
Hello, everybody. Thank you, Nat. Thank you all for joining us on our webinar today. We're going to talk about different challenges that engineers confront today when they're designing systems, subsystems, or integrated circuits. Often when I'm out talking to customers, I'll hear things like how fast the designer can correlate their signal integrity models to the real world when they're during bring up is something that can take a lot of time for them. Obviously, they want to shorten the cycle so they can get their product out ahead of the product window, the product viability window. The more time that you're in the market, the longer you'll be able to sell your product. So the quicker you need to bring these things up. So this conversation is an effort to facilitate that. Also, these systems can require several different high-frequency interconnects, and each one of these interconnects can have its own loss. So reducing the amount of interconnects helps in a couple of ways. One way is to reduce the signal loss budget that's required by all these different interconnects. Another way is to reduce the required real estate on a printed circuit board. In addition, some of these components can be soldered down, and when you solder something down, it's kind of a sunk cost in the program. It's difficult to recover, and if it isn't soldered correctly, then you may have to do costly or time-consuming rework. In addition to that, when you solder down components, you have to plan ahead to know exactly which signals you want to measure or probe during functional bring-up. In a lot of cases, you may have some measurement nodes in various places on your printed circuit board, but one test validation process may not require an interconnect in certain areas that another test may require an interconnect. So when you have to solder these things down, you lose an element of flexibility. So we're going to talk to you today about one of the things that we've come up to help solve this problem. We're going to talk about the TR Multicoax Series, which has been on the market now for about 2.5 years. We've done a fair amount of signal integrity development to increase its bandwidth capabilities and also to decrease, in some cases, its cost. And like signal integrity capabilities for applications that require less frequency, for example. I wanted to mention that in the onset of this product, we called it Terminate-R, Terminate-R, and TR is synonymous with that. So you may hear me refer to it as Terminator in certain cases, as it's printed on the molded parts that we make, but TR and Terminator are the same thing. So when we started out to develop the Terminator, signal integrity was the most important thing to us. We have a very, very short interconnect, and we wanted to take advantage of that and make sure that we can translate that super short interconnect into very high bandwidth capabilities. So the product was called TR Multicoax Series. It came out as a 40 gigahertz product. We've since enhanced its design through modeling and measuring, and we're able to get 70 gigahertz through it today. It's a high-speed connector, the highest speed multicoax connector on the market. We worked very hard to facilitate our customers' design of this product. It's solderless. So you can put a footprint on a board and move it around the board, even if you don't anticipate that you need to measure it in one part of a functional test, for example. Another side of the functional test may require a connector there, and you don't have to put that soldered piece down ahead of time. We have quick connection. We'll show you a bunch of different ways to connect this thing to the board. A huge space savings over SMPs, not let alone SMAs. SMAs are even larger. And since it takes less space, you can get closer to the device, which means you have less signal trace in the printed circuit board, which I'm sure all of you have experienced are not very good transmission lines. And also failing snap-in connectors. It's a common thing that we hear about a soldered down connector that is a half D10 or a full D10 or no D10, and it wearing out and not holding the cable, so repeatability becomes an issue with some of these single SMP designs. Another advantage of not having to solder down is you can use the stuff across multiple programs. So when you move on to the next program, your cables can stay with your lab and be used exactly on the next program. And if the board cross-section remains the same, then all that work is already done for you. All the implementation, heavy lifting has been done. So some of the applications we're talking about is semiconductor design and test. That's obviously our flagship application where this was developed for customers with multiple high-speed SerDes lanes. Automated test and measurements coming on really strong as our second biggest category. We make some blind mate connectors that can attach to your duct board and allow users to make 28 gigabit interfaces, for example. Communications, Nat had mentioned quantum computing, where magnetism is a big no-no and they got to test at cryogenic temperatures. We also have a lot of defense and aerospace applications. We make connectors for phased antenna arrays. We use this technology to test ASIC substrates directly. So instead of using a probe card, they just put coaxial connections right up to an ASIC substrate. We're adapting this technology to be a chip-to-chip twin-ax interconnect, which will be available shortly. And that's going to be a relatively inexpensive OEM version of this thing that transmits very high frequencies outside of the printed circuit board to replace backplane, very high-speed transmission lines in backplanes. We also have applications in CAT scan and ultrasound. So as I led off saying that signal integrity was our number one characteristic that we wanted to be sure that we got right. And in doing so, we've acquired some tools and some resources to do that. We have our full-time signal integrity engineer right now. We also have a consultant that we use. We have 3 network analyzers, one out to 67 gigahertz. We have HFSS here, version 17, and all the tools to bring models from SolidWorks into HFSS even after they're deflected. So we can take a spring and we can run FEA on it and compress it and then export it into HFSS and run signals through it. So we can have a real-time understanding of how signals are behaving inside these compressed elements. And that's helped us. This is what has enabled us to increase our bandwidth. We also have all the cal kits and the cables and all the stuff you expect to see in your lab every day. So just a high-level performance slide. This is a measurement of just the TR interface between 2 coaxial cables. So in some of our ATE applications, we make these connectors, and we'll get into this in a little bit, where we just put an interface between 2 cables. So instead of connecting or disconnecting 24, 48, 64, 56 cables, we can do this with one connector. And what you're looking at here is a measurement of the electrical performance of just the interface without a printed circuit board. So this is the best you can achieve today with our manufacturing materials and our geometries today without the losses that would be associated with a printed circuit board. Now we have a lot of modeling and a lot of real-time measured data into a printed circuit board, and we'll show you that too. And we contend that it does work to 70 in a printed circuit board case, but we wanted to isolate just the interface because we want to tell you about just the interface today and the best you can do. What you're looking at here is insertion loss and return loss. On the bottom, we've got frequency, obviously, and on the left-hand side, we've got decibels, S parameter decibels coming down from 0. We see insertion loss there, and you can see that that first line is very linear with respect to frequency. There's no resonances. And then the underneath that, you see the return loss. In the return loss, we're looking at minus 15 all the way through 70, but really minus 17, which equates to about a 98% efficiency on your signal. That's about 1.33 in VSWR, so fairly good signal return loss. The next slide is a magnified version of the insertion loss. So the scale on the left is only 5 dB, so you can kind of see how that's affected. So you've got 6 inches of cable there, and the lion's share of that loss is due to that 6 inches of cable. About a half a dB is due to the interface. And we have other test data where we can show you where that's isolated, but here again you can see that there's no resonance and it's out to 67 gigahertz. The next slide is return loss forward and backwards. This is also from the first graph that you saw, and as I mentioned before, we're looking at minus 17 dB. at about 35 gigahertz, and then not again until about 60 gigahertz. So that's a 98% efficient signal all the way through 70 gigahertz. And we're working to make it higher. We can simulate now to 100 gigahertz. So we feel like our limit on our interface currently is 85 gigahertz, but we feel like we've got other knobs we can turn. This is just where we're at today. The next slide is the noise floor. So this is, again, just the cable-to-cable measurement, and you can see a little schematic off to the right there. If you add a printed circuit board, you're going to get a lot of more crosstalk inside the printed circuit board. But this is to show you that our interface is metal and shielded, and if you just use metal and shielded stuff, this is the noise floor that you would see. And you're looking at better than minus 70 dB through 70 gigahertz, really minus 80. So when you add a printed circuit board, a lot of that stuff goes away, but this is fairly decent from the cable perspective and the interface perspective. Next slide. So second only to signal integrity is repeatability. Resounding information that we get from our customers is, geez, I have tried some multi-coax solutions in the past, but every time I plug them in, I've got a different insertion loss or return loss or different signal characteristics. Or I have SMPs and when I snap them in, sometimes they're loose and I don't know which one's loose and I got to go back and tighten them all up just to get the same signal integrity I had before. It's hard to have an S2P file or a touchstone file that matches a connector when the reality of that connector is not behaving that way. So that kind of adds a whole bunch of time in the design cycle, kind of ironing these things out. So this next slide shows repeatability. On the left there, that's 56 different TR channels on the same printed circuit board, a measure of return loss. So there's 4 total transmission lines on that printed circuit board, so there's 4 characteristic curves that you're seeing in there, overlaid over and over again. The TR itself is fairly consistent, as evidenced by this graph. Now this was taken before we got the 70 gigahertz. We plan on working this out to 70 gigahertz as well. On the right side, you see the same TR cycled 1,000 times. We didn't stop at 1,000 because it broke at 1,000. We stopped at 1,000 because we felt like that was enough. And when a TR fails, it goes wide open. The spring has a fatigue failure on the contact, so you'll see it'll go wide open. There'll never be any question. It's not like this starts to fade to bad. It's going to stay like it is when it's brand new until the end, until it comes wide open. The next slide is the insertion loss of the same. On the left, again, 56 different channels. This shows you repeatability from one terminator assembly to the next, cable assembly to the next, block assembly to the next, all the printed circuit board being the same. And again, on the right, 1,000 cycles measured at 0, 50, 100, 500, and 1,000 cycles. Again, out to 40 gigahertz. So some of the other things advantages that we went for is obviously the reuse and the tighter densities. So we have customers in 2 general baskets. One basket where they have super stringent requirements for signal integrity, and then another basket where they're just flat out of room on their printed circuit boards and they've got more channels, and the printed circuit board has to fit in a defined area. So they have to get those signals off of there, and density becomes an important issue even if they're under 20 gigahertz all day long. So those kind of customers we are able to help out as well. And that's hence why we came out with the 20 gigahertz version. So again, no solder down leave behind. So some of these RF connectors, I'm sure you guys are aware, can be quite spendy. And if you have to leave something behind, even if you have the intention to take it off later, it seems to be less important when the program's pushed through and things make it to production and you're on to the next thing. And this way you don't have to inventory anything and you don't have to worry about the throwaways or the leave behinds. So this next slide speaks to the different mounting configurations that are available on the Terminator. So the top left there, that's the straight mount. That's the standard one that we started with. You can see this on about 100 mil pitch That one's 16 channels that you see there. It's screwed down. It has those 2 screws that you see are captivated. So while you remove them from the board, they're not going to fall out. So you don't have to worry about metal stuff floating around in your electrical system, shorting stuff out. The next one over on the right side there is a right angle version. So it's made with the same technology, same interface, takes the same footprint as the straight up version. It's just manufactured in such a way that the cables come out at a right angle. And the total height of your connector is less than 200 thousandths. The bottom left is quick latch. Quick latch was made in response to folks that have a lot of systems they want to test. So let's say you have 4 or 5 functional boards and you want to measure one parameter on all 4 or 5 of those functional boards. Instead of undoing 16 different SMAs or SMPs on each board and running through it, you can just use these spring-loaded latches to anchor onto the board to get a quick disconnect or connect, however you're looking at it. This one also uses the same interface, and since this is a spring-loaded design, it compensates for board thickness variation. It works on this design from a 63 thousandths board to a 250 thousandths board. If you have a thicker board than that, then we can change the latches and make it accommodate that. But the standard design is for 60 to 250 thick board. And it'll always have enough spring force on there. The last one is the bottom right, and this is the one that the graphs are taken off of, and it's the blind mate interface, cable to cable. So in this particular case that you're looking at, our customer is building their own tester, and they needed to disconnect 28 cables, 56 cables, and they only had so much area to do it in. They've got a test dot board on one side of their tester, and the other side is a custom-made rack that has RF modules and mixed signal modules and power modules and all these modules they can add depending on what they want to test that day or in that test cell. And this is the RF part of it. So they used to be limited to 16 32 channels. We've stuffed 28 channels into this 1/2 inch by 1 inch block. So now they got 2 of those, 28 channels each. They're up to 52 channels, 56 channels, excuse me. We want to take them to 64 right away. So those are the standard types of mounting configurations for Terminator, though there's new ones coming along all the time. We're already working on a 45-degree angle that can be ganged up so that you can put 20 of them back to back on a board, all launching at a roughly a 45-degree angle, and you can fan the cables down and keep the whole thing less than an inch, inch and a half thick. So stay tuned for that one. So some variations in the mechanicals we can go through here. We've got a standard 1, 2, 4, 8, 12, 16, and 24 channel versions available as standard. We do custom a lot. 28 channel, we just showed you a 28 channel. We did a 64 channel for an application in Japan. So if you got a special needs application and you want to get really high signals through something repeatably, let us know. We can design something special. As I mentioned, standard pitch is 2.54 millimeters, 100 thousandths. We can go smaller than that. We do go smaller than that, but with the flexible cables, that's where we're at today. Compression mount to the board. Haven't hit that one into the ground enough. It's nothing to solder down. So just put the footprints where you think you need to all around your device or wherever you want your test leads to come from, and put the connector there or not. Test the channel 7 or not, but you don't have to worry about it when you're laying your board out. We offer standard 6, 12, and 24-inch length cables. We also are pretty popular with a 3-inch because people want to keep the smaller cables to a minimum length so that they have a minimum loss. And then we have other customers that don't really care about loss and they want a 36-inch cable so they can go from their functional test system right to the VNA with no junctions, no interconnects, adapters. And so we've done that too. So if you have a special cable length, we've talked to you about that. Happy to. We do phase matching. Our standard is plus or minus 2 picoseconds, but we also do plus or minus 1 as a special order where it becomes more or less a sorting operation. But plus or minus 2 is our standard. And that's plus or minus 2 across the whole connector, all the connectors, not just any 2 pair. We rate the thing to 1,000 cycles, and as I said, we didn't stop because it failed. We stopped because we felt that was enough cycles. The interface is replaceable. It's held on by 2 screws, so that part can be replaced on the field very easily. All you need is the right screwdriver, which we send out, I think, with every order that send TR anyway. Bear with me a second here. So, cost benefits. So we talked about the no solder down. So if you picture a big functional test board with several hundred SMAs or SMPs on it, the dollars there begin to stack up pretty quick. So that's pretty simple message there. 20, 40, 60, 70 gigahertz. Now, one thing I didn't mention is if you design this thing for a 40 gigahertz operation and it moves to 70 gigahertz, if it's optimized ultimately for 70 gigahertz, nothing needs to change on your board. So all you need to do is change the connector. So once you've got it laid out, if we use 70 gigahertz as the parameter for your optimization, then you can use any one of the connectors. The other point I failed to mention on the different configuration application slide is the right angle and the quick latch and the straight up all use the same footprint. So if you buy a right angle straight up 8-channel, you can use, and turns out you got a heat sink you got to put on top of the thing. 6 months down the road, you can switch to right angle without changing your footprint or anything. Same with the quick latch. The quick latch just requires a couple of routed holes in the printed circuit board, and it's the same 8-channel, same stack-up configuration. So tighter footprint, less real estate, field replaceable interface we mentioned. No downtime for our RMAs. You could buy 1 or 2 extra interfaces and have them at the ready. And we're so confident that you're not going to destroy these interfaces in standard function that we replace them for you for free for the first year, which effectively means just repinning them. If the brass plates are okay, then the only associated cost really is refilling it, repinning it. So we talked a little bit about our modeling capability. So in order for a customer to be successful with a Terminator, you have to model your board stack in the launch, as you do with any high-speed RF connector. So we offer that service for you. If you send us your board stack and you tell us which layers you want to launch off of and what your dielectrics are and how thick they are, we'll put it through an optimization in HFSS, which will kick back the optimal cross-section for you. We do it here. A lot of our customers want to do it for themselves. We can also sell you that model. That model is actually done by our consultant, and he has a parametric model, so he has to dumb it down. So there is a little bit of a charge there, but we highly encourage you to take advantage of our optimization services, even if you want to optimize it yourself. It never hurts to have another set of eyes looking at that optimization just to make sure that your numbers and our numbers match before you go to fab. All the work up front in making the printed circuit board footprint as good as it can be will pay off in spades and time down the road. The only applications in the history of the Terminator that have been troublesome are ones where the footprint was not followed properly. So use us as much as you can to help you design the printed circuit board. We'd even be willing to talk to you fab house, but certainly to your layout guys. So launch optimization, footprint layouts. We have application notes. We have one large application note that covers all the information you need to know about Terminator, from environmental performance, signal integrity, footprint layouts, usage, care, all that stuff. And then we have smaller application notes which kind of divide that out, and like a quick start guide and a guide for replacing your interface. So these are all things that are available to you on our website, as well as YouTube videos, which we're getting more and more all the time. And also, you'll have direct access to the engineering support. We're actually in the process of starting a field applications engineering department. But right now, you get standard engineering, standard signal integrity, and you can talk to me or the director of engineering anytime you want. So right now we're going to go through a couple of quick case studies. And these are cases where we have Terminator has been a success. And the first one that I mentioned is the standard that got us into this program and into this product category, which we love, by the way, is high-speed SerDes on a very big BGA device. So this particular guy had 400 channels that he had to measure. So 400 channels is just impossible to lay out all those SMPs. So what happens if one of those SMPs floats or gets not soldered properly and you got to rework the whole board? What happens if it's an important channel? And where are you going to put those 400? And if you put those 400 on there and you pay $10 each for them, you got $4,000 in sunk costs on your printed circuit board. So we replaced all that with just this gold footprint. And now you can see the two terminators off on the top side of the board, but they can move them around to all those footprints that are closer to the device. It makes measuring the performance of those SerDes channels a lot easier. And take it one step further, you could have used the quick latch and could have stepped around it instead of using the screws. Although the screws is a very quick method in itself, and we definitely give you a screwdriver to mount those on. So the next application is kind of one I touched on a little earlier, is where the customer had several boards, several systems they wanted to test. They didn't want to keep connecting their connector to their VNA over and over again, or snapping and unsnapping SMPs. So they bought a quick latch. And you can see the quick latch cutouts next to the footprint there. One is larger than the other, so you can't put it on backwards. Also, the guide pins do the fine alignment. The latches just do the rough alignment. And it, like I said, it compensates for all your varied thickness in boards. So this next case study was the right angle. This was the birth of the right angle. We had a very prominent IC manufacturer up in Toronto, Canada, who developed ICs for other companies. And they were developing this switch, and they had this huge heat sink on it. And they were trying to figure out how they're going to get their signals closer to the dot and still get their signals outside. And the right angle was the solution. So this one, again, offers the same footprint as the standard straight up 8, but it's in a right angle configuration. So if you got a big heat sink on there, you can still get very close to the device. I think I mentioned it was 212 mils for the height of that right angle, but it's there in the presentation and you'll have all this. And you can always bounce back questions at a later date. The last application, this is the cable to cable. So this is where a customer had a probe card that went off to their tester, and the probe card had 48, I think, channels on it. And each one of those channels was an SMA, not an SMP, a screw down SMA. So in order for them to change their duct card, they had to unscrew 48 different channels. It took them a long time, as you can imagine. So we created a 48-channel blind mate connector system that was essentially a little manifold that they put a connector pretty close to the duct card, and they could easily screw it on and detach it from their tester anytime they wanted. And they're actually getting as good signal integrity as they would if it was a straight cable, as you've seen in the graphs previous in this report. So to demonstrate this signal integrity capabilities, we understand that, you don't want to take our word for it. I wouldn't take our word for it if I was you. So we offer an eval kit that you can use and measure yourself. And in a lot of customers' cases, they'll put a footprint off to the side of their next design, one that's not functional or partial to their design. And they'll model and optimize that footprint and just go out to an edge launch connector so you can see how our technology would work on your board stack. So these are some of the things that we offer to help you mitigate the risk of trying a different connector style. We understand that once you head this route, it's hard to turn around, and we want to mitigate that as much as possible. So quick little summary here. Signal integrity is our focus. We work every day to improve it. We're going to continue to improve it. I wouldn't be surprised if we have our next network analyzer in a year, since the first one only lasted a year. So repeatability. very important to us. We have all the data. If you guys want to see the raw test reports, you're welcome to. This is a solderless compression mount connector, relatively high density. We're already down to 0.8 millimeter pitch with this technology, but we do 2.54 as a standard. We do all kinds of customs for every different kind of environment you could want. And we lower your total cost of testing. Even if you only got 16 SMPs, and day one, it's not cheaper. Day 30, it's going to be cheaper when you don't have to build your second board with your other 30 SMPs and your other 30 SMPs. So the cost benefit's going to be there. If it's not there instantaneously on day one, it will be there through time and solder down materials at a later date. Just mostly attributable to the ability to reuse across programs. So I think that's rounds it out for today. I think how are we doing on time, Nat?
Looking good. I think that thank you everyone for taking the time to run through the presentation with us. That's going to conclude the presentation segment of the webinar, but we'll now open the floor up to a few of the questions that you've been sending us throughout the webinar for Gordon. I've been compiling a list from the questions box here, so I'll pick a few at random. And if your question doesn't get asked in today's segment, we will have someone from Arden follow up with you directly. With that said, Gordon, looks like one of the first questions we have here is, how do I de-embed this connector?
So we will send you a S2P, S4P touchstone file depending on what you need. If you're using differential and you need to understand crosstalk between two channels, we can do that too. We have S4P files at the ready, or S2P files at the ready for all the cable lengths. So these are measured with the same fixture that you saw the results, so there's no printed circuit board. So we'll give you the de-embed fixture that you can add to your loss budget and see how you come in when you do your simulations.
All right, thank you. Another question we have here, the question is, there are other connector companies in the market that are similar. What makes your product different?
So there's quite a few different companies out there doing different things. So if we start with SMAs, it's density and signal integrity. If we talk about single channel multi-coax connector types, it's signal integrity and signal repeatability. If we talk about SMPs, it's repeatability, and in a lot of cases, signal integrity. If we talk about the guys in Switzerland that are making the multi-coax with the solder down block, it's the cost of that solder down block. So from a 30,000 foot perspective, I say that we have signal integrity advantages over all of these companies. But then as you step it down a little bit, we have a little bit of an advantage over each one of these companies, either in density or in signal repeatability and or cost.
All right, great, thank you. So another question we had here is they ask, TR's compression mount, how do I keep my PCB from bending?
Yeah, so we supply with all our terminators a stiffener block. The stiffener block is recommended for printed circuit boards that are less than 1/16 of an inch thick, so 63 mils. The stiffener block is immediately exchangeable with PEM nuts. So as soon as you go up higher, like a 93 board or a 100 board or 125, the user can merely press in PEM nuts on the backside, and they don't really have to worry about board warpage. The Terminator is relatively short in length, so the amount of board that is pulling up to it is short, and it stays flat on that section of board. So the short answer is stiffeners in the case of a thin board or a warped board, and we use PEM nuts in the case of a thicker board.
Okay, and I guess kind of following along with that, actually, what special footprint provisions or plating do I need?
So we recommend hard gold, but we know that ENIG is very popular. And then also we have customers that use immersion silver for very high frequency applications where they want to eliminate nickel. So our general answer to customers is, as long as it's a noble metal, anything but solder can be used there. So silver isn't necessarily noble, but we have such a small contact point that oxidation doesn't get under there. But solder solder oxidizes readily. It's not flat. There's all kinds of reasons why solder is not a good surface. So we recommend either hard gold, ENIG, or immersion silver.
All right, thank you, Gordon. Another question we have is, can you expand upon how TR can save cost compared to surface mount components?
Well, it's just goes back to channel count more than anything. Channel count, program count, I guess. So if you, in that other case, you have 400 SMPs, I mean, the cost savings is immediately visible when you go to buy those SMPs, especially if you have one of them that doesn't solder properly and you got to rework the whole board, then you're easily saving lots and lots and lots of money. But it's more of a challenge when you're down to 16 pins, and then it becomes frustration time of plugging in and unplugging all those contacts, the distance that you can get those contacts to your DUT so that you can be sure that your functional test system correlates with your HFSS model that you did on the onset. So time in that factor, and also the reusability across programs. So if you, in the picture here, for example, if he went on to his next program, he's going to carry those same cables with him, and he doesn't have any sunk costs that he's got to throw in the garbage can to let sit on a shelf.
Great, thank you. So another question that's come through is, you've shown some impressive data and loss rates. How can I verify your measurement results?
So that goes back to the eval kit. I kind of jumped the gun on that one a little bit. So we'll send you an eval kit where it has has some traces on it so that you can measure the loss of the traces yourself and understand the board loss. But you can also do a through measurement, which is what we publish for data, is we'll give you through measurement results on the board with a connector and an edge launch, either a 1.85 or a 2.92 edge launch. So we encourage you to verify your results either on that vehicle or, as I mentioned, put a coupon off to the side of your next design and just go to an edge launch connector. That way you don't have any real risk in it.
Great. And the last question we have here is, what tools are required for installation?
Just a Allen head screwdriver, M2 Allen head. So 1.5 millimeter Allen head screwdriver is all it requires to put this thing on. In the case of a quick latch, nothing. Just your hand and the right board design.
Great. Well, thank you very much, Gordon. Okay, folks, that's it for today's webinar. We do want to thank everyone for joining us. As we mentioned at the beginning of the webinar, it is being recorded, and we'll be sending out that recording link to all the attendees, as well as the slides. I do want to make note that in the handout section of your GoToWebinar portal there, you should be able to download the TR datasheet if you wanted to see some additional information on the product. And we also have our contact information up on the screen here. If you have any additional questions, please feel free to reach out to us. We're more than willing to help and excited to hear from you. So that's it from us at Arden. Thanks to everyone, and have a great day.
Hope that you enjoyed it. Thank you very much.